I hate
There.
data.
Wait.
Oh,
It's going.
Oh,
Okay. No. All right.
I'm with
So, here's the story. So now 15 kind of through 18 is going to be one kind of big idea. So here's what's going to be different on these questions. But it forms a nice framework for how energy is changed. So instead of oscillating vertically like this, imagine that I would take this mass and I would compress it and I would do some work because I would push the spring and I would store some us. And then I would let go and this thing would begin to oscillate back and forth. Now obviously this only works on a frictionless surface. Okay? So imagine this is oscillating back and forth on a frictionless surface. So we don't have to worry about UGG, so that's why mathematically this makes this a little bit easier to deal with. So you are going to store some us, and this is the concept that we talked about yesterday. Generically, how do you calculate us? 1/2 kx squared. Okay? Generically, 1/2 kx squared. So x could be any displacement from the equilibrium point. Now, if it's at its maximum displacement, instead of x, what are we going to use? A for amplitude. So if we're at that maximum displacement, us, which at that point, that's the only type of energy that we're going to have. Why am I not going to have any kinetic energy? Stop to change the direction. So us is going to equal my total energy at that point, which is going to be 1/2 K A squared. Now, that only works if you're at one extreme or the other in terms of the amplitude. X works at any point. A only works when you're at the extreme. Now, if I'm in the middle, what's the value of X? 0. So how much us do I have? Nada. But what do I have a maximum of? Velocity. So in the middle of the oscillation, I have no us, so all that energy is going to exist as what? KT, and KT is 1/2 M. Now, I'm going to put that as V max squared, okay, because that's when it's going to have its maximum velocity. So, that in the middle is also going to equal the total energy that could exist within the system. So what that means is that the total energy that I could have, energy total, could equal 1/2 Ka squared, because if I'm on the extremes, it's all us, right? That could also equal 1/2 K, or 1/2 M, V max squared. Okay? So here's the other reality of what this means, is that at any point in between, the total energy that I'm going to have is going to equal some value of us plus some value of KT. But if you look at the extremes, if I'm in the middle, I don't have any us, and it's all kinetic, so that's 1/2 mv max squared. If I'm at the extremes, I don't have any kinetic energy because I don't have any velocity, so that's going to be us. So if I know either my V max, or if I know what my amplitude is and the K value, I can figure out what everything else is. So like if I know that my amplitude is 0.05 meters, and I know the spring constant, I can figure the total energy of the system. From there, I can figure out what the maximum velocity would be if I knew what the mass is. But here's the bigger truth. So at any point in between, if I know what the position is, say my amplitude is 0.05. So if I'm at 0.02, I could figure out how much us I would have using 1/2 kx squared. From there, I could figure out how much kinetic energy I would still have. I can figure out how fast it's going to go. Okay? So that's the bigger picture. Now, when you get to number 18, so at this point, what I just said, you should be able to answer 15, 16, and 17. Okay? Literally, I just gave you the answers to 15, 16, and 17. Okay? Literally, just gave you those. So, get those answers, let me draw the graph for 18 and 19. Just keep it going.
What I do is oh yeah.
Okay. So, on 18 and 19, this is all about like the terminology in terms of what we're talking about with types of energy. So number 18 says, assuming that there is friction. Okay, so initially up to this point, we've neglected the effects of friction. Now there actually is friction. So since there is friction, as this thing oscillates, what's it eventually going to do? It's going to stop, right? It's going to slow down because there's friction. Okay, and we're going to take some of that energy and it's going to be lost as heat. Okay, so it's going to heat things up a little bit. So on 18. It's got the energy time diagram for just the mechanical energy of the block. So when on the AP exam, the terminology, when they're talking about mechanical, they're just talking about the kinetic energy aspect of this. We're not worrying about the spring, okay? All we're talking about is literally like mechanical energy of the system, which is just kinetic. So since it's starting at its largest amplitude, so imagine that we're just going to keep track of the kinetic energy. So first off, is my kinetic energy ever going to go negative?
Oh, no.
Why not?
Velocity squared.
Because velocity is squared. Okay? So on 18 on this graph, I don't have to worry about going into negative energy because of the fact that it's 1/2 mv squared. So is this graph on 18, because it wants the mechanical energy, and you're starting at the amplitude, the farthest point, will there be any initial kinetic energy?
No.
No. So that's going to start at 0. Okay? So as it slides, what's it going to do?
Go up.
It's going to increase. But then, after it passes the middle,
It go down.
then it's going to start to slow down.
And then
Okay.
it goes back up, but not as much.
Why not?
Because it loses energy to friction.
Yeah. So the next one is going to go. You are dead to me.
I'm so sorry.
Me?
Air molecules.
I was a goat.
Mm-hmm. So eventually, what's this graph going to do if you went out far enough?
Go to 0.
Yeah, eventually it's just going to go to 0.
He
because
did,
it's gonna
yeah.
stop. So on 18, all you have to do is draw it as a series of decreasing hills. Okay? All you have to do. Now on 19, assuming that there is friction with the block, draw an energy time diagram for the system consisting of both the block and the spring. Okay? So in this situation, instead of just the kinetic energy, we're going to be talking about the sum total of all of the energy. Okay? Just not the mechanical, but the sum total of all of the system. So we're still going to pull it out to some maximum amplitude. But because now we're considering the spring, okay, it's not going to start at 0. So it's going to start here. Now, riddle me this. If there was no friction, let's just do the what if. If there was no friction, what would this graph do?
Horizontal line.
It would just be a horizontal line. Okay? Now, would your mechanical energy, your kinetic energy be changing? Would your spring energy be changing? But they're still going to add up to the same value. But because there is friction, what's this graph going to do? Yeah, it's going to go down, something like that. That's all you have to draw. Okay? Do not make 19 complicated.
Yeah?
Okay? Got that one. Okay. So, stop that for a second.